it is the title at page 143. There is a sentence. What is the condition for conservation of mechanical energy? And you learned what conservation means. Conservation, if a quantity is kept constant, so we say that that quantity is conserved. So conservation of mechanical energy, so then mechanical energy must stay constant in some situations, in some conditions. That condition is for an object which can rolling up or moving up or down on an incline, or just you throw an object up and then it's moving up and then going down. So if only force acting on this object is the force of gravity, gravitational force is the only external force acting on that object. So in this case, the total mechanical energy, so which is the sum of kinetic energies, all types of kinetic energies, plus potential energies, which is all type of potential energy as well. So some of these energies must stay constant. So total kinetic energy means kinetic energy plus potential energy. So it must stay constant, remains the same as this object is moving. This is what conservation of mechanical energy is. Yeah, there mustn't be any energy which can cause object to lose energy. There mustn't be any force which can cause object to lose energy, like friction, like air resistance, like these two are in fact are the basic reasons for an object to lose its mechanical energy. So we are going to neglect these energies while we are going to neglect these forces, and friction force, but which one? Kinetic friction, because remember when I was explaining to you about the friction forces, I told you that static friction is the reason of the motion, but kinetic friction is the reason for the stop. So kinetic friction causes object to slow down by decreasing object's mechanical energy. That's why. So I'm talking about the part which is kinetic friction, because static friction helps us to, or helps an object to move, or help us to move. So it is not causing a loss of energy, but kinetic friction can cause a loss of energy. So that's why we are going to neglect kinetic friction or air resistance while while we are talking about conservation of mechanical energy. The first problem I solved is a revision problem about the conservation of mechanical energy within the context of 11th grade. So, and maybe you remember this solution from the 11th grade as well. If a block with a mass of 4.1 meters starts from rest at a height of 2 meters and slides down a 30-degree slope. Now, in here there is a mass at the top of an incline. This is the mass. And this mass is 4.1 kilogram from rest. So we are going to release this object from rest initial. So linear speed is going to be 0. So slides down. In fact, every problem you solved last year was about this. You assume that object is sliding down. And you studied only translational motion of the object in the 11th grade, even maybe they didn't tell you, your teacher didn't tell you, because it's not in the book directly. This is translational motion. So only sliding down is only about the translational motion. Object will start moving on this incline, along the incline. So then what is the translational speed of the ball when it leaves the incline? And when this ball comes in here, so what is this final translational speed of the ball? Not ball, of course, it's the block. I changed this question from the 12th grade to 11th grade, so I forgot some words to change. So what is the translational speed of the block when it leaves the incline? So total mechanical energy conservation is that as this block is sliding down along this incline, at every point on this path, total mechanical energy of this block will be same. So at the top, at say at point A, in here say at point B, in here say at point C or D or bottom, sum of kinetic energy and potential energy, which is total mechanical energy, must be the same at every single point as this block is sliding down. So, but I don't care about B, C, D. I only care the top and the bottom, because these 2 points will have same amount of mechanical energy. First, I will calculate the total mechanical energy at the top, which is kinetic energy plus potential energy 1/2mv top. Yani translational speed at the top squared plus mgh, which is the potential energy due to the altitude or height of the object. But we know that object is released from rest. That's why this term is going to be 0, which means total potential energy at the top only equals to potential energy, gravitational potential energy. Total mechanical energy at the top equals only gravitational potential energy of the object, because object is released from rest. This term becomes 0. But at the bottom, when the block arrives to the bottom, this time it gains kinetic energy. Kinetic energy is 1/2mv bottom squared plus mgh. Because altitude height is 0, potential energy becomes 0. So this time second term becomes 0. That's why I will write total mechanical energy at the bottom is equal to 1/2mv bottom squared. And according to conservation of mechanical energy, so this mechanical energy must stay constant. That's why total mechanical energy at the bottom and total mechanical energy at the top must be equal to each other. I will make them equal and I will calculate the translational speed at the bottom. So 1/2mv bottom squared is equal to mgh. These m's will simplify in both sides of the equation. So v bottom squared will be, get this 2 on the right side as multiplication. 2gh is v bottom squared. Get the square root. V bottom is 2gh, root of 2gh. 2gh is given in the question as 2 meters. When you write 2, you will calculate translational speed of the object 6.26 meter per second when a block with a mass of 4.1 kilogram start from rest from a height of 2 meters, slides down 30 degrees slope. That angle is 30 degrees given. What is the translational speed of the ball when it leaves the incline? So it is 6.26 meter per second. This is the 11th grade part. This is what you should know from 11. If you don't know, I briefly explained to you what conservation of mechanical energy is. But this time, in the 12th grade, we are not going to slide down an object. We are going to roll down a sphere, a cylinder, a ring, or something like this. Sample 2E is now we are going to apply this conservation law to a rolling object, a rolling sphere, a solid ball with a mass of 4.1 kilogram and radius of 0.05 meter. Start from rest. Again, remember, I gave the same numbers because I will make a comparison at the end. In the end, that's why I give the both this question and that question have masses are equal 4.1 and also radius is 0.5. Starting from rest, yes. From a height of 2 meters, yes. So rolls down at 30 degrees slope, yes. What is translational speed of the ball when it leaves the incline? This is the question. Now, as I said, this time I'm going to write mechanical energy at the top first, energy at the top. So we know that energy at the top is total mechanical energy means potential energy, object's potential energy, mgh, plus total kinetic energy. Total kinetic energy includes what? Kinetic energy, translational kinetic energy plus rotational kinetic energy. And 1/2 mv squared is translational kinetic energy plus, if object is rolling, 1/2 I omega squared. However, this block, this sphere, this solid ball is released from rest, which means initial translational speed is 0. Or if the translational speed is 0, which means initial angular speed is also 0. That's why these two terms again becomes 0 at the top, because you release them, this sphere, this ball from rest. Initial kinetic energy is are zero. Only potential energy this ball has at this point, say that point at point A. But then this ball starts rolling down, so as it is rolling down, what will happen? Its potential energy will decrease. By the time its kinetic energy must increase. When it attains the bottom of the incline, this ball will have a total mechanical energy, say that bottom, E at the bottom, so is equal to, this time mgh becomes zero because altitude becomes zero. But now this ball will gain kinetic energy, but not only one type of kinetic energy, both rotational and translational, because this ball is spinning about, turning about its central mass 1, and also translating. That's why we are going to write 1/2 mv squared, which is the translational kinetic energy, plus 1/2 I omega squared. So this omega is the omega final. In the beginning, omega initial is 0. So we are going to find that omega final, or we are going to find this v. But to find that, you should convert one of them to another one. You should write omega final in terms of v, or you should write v in terms of omega final. So we know the relation between them because we learned that for a rolling object, every type of rolling object, omega and translational speed of the object is related. Translational speed is equal to r times omega, just similar to the equation of tangential speed. R omega is v tangential speed. For a rolling object, this equation also valid. Translational speed, which means the speed of the center of mass of the object, is equal to r times omega. R is the radius of the object, and omega is the angular speed of the object. So then, because here translational speed is the question, Vt is the question, so instead of v omega, I am going to write omega divided by r. Omega is going to be v translational speed divided by r. I'm going to insert this Vt over r in here instead of v final, omega final in here. So I will rewrite this bottom part because everything is about this bottom, because a longer calculation will be in the bottom, mechanical energy in the bottom. So 1/2 mv squared. There is nothing wrong about this one. It's okay. We are not going to do anything with this term, but next term I have to write I. What is I for solid ball? So it is 2/5 mr squared. This is the moment of inertia of the solid ball. So then I am going to insert this I into this equation. 2/5 r squared. Then instead of omega final squared, so let me square this, both of them, square them. Omega final squared, I will write vt squared. Let me write just v, because 2 vt's, 1 vt is not good. So v squared over r squared. So then you are going to see that these r's will simplify and these 2's will simplify. If you write this mechanical energy at the bottom, it becomes 1/2 mv squared plus 1/5. This becomes 1/5 mv squared. Now I wrote the equation in terms of v because v is asked. I can add them and I can find energy at the bottom as 1/2 plus 1/5, which becomes 7/10. If you add them, 1/2 plus 1/5, because mv squared are common, so it becomes 7/10 mv squared. Then I know what total mechanical energy at the top. I know what is the total mechanical energy at the bottom. According to conservation law, these two energies must be equal to each other. 7/10 mv squared must be equal to mgh. Again, m's will simplify on both sides. I am going to write equation for v squared. V squared is equal to this 7/10. Take to the right side as 10/7. 10/7 multiplied by gh. Get the square root. So you will find what the translational speed is. Root of 10 GH, G is 9.81, H is 2 meters height, divided by 7. Don't forget the bracket inside the root. So you will get the answer as 5.29 meter per second. As you see, translational speed of this solid ball is 5.27. But in the first problem, when you release a block, its translational speed was 6.26. So as you see, when it is not rolling, when it is sliding, so even you slide them from the same altitude, even the masses are the same, even the altitudes are the same, even the inclination are the same. So all are the same, but in the case of the sliding, so translational speed is 6.26, but in the case of rolling down by a solid sphere, translational speed is 5.29. As you see, in rotational motion, when it's rolling down the incline, translational speed is less than the sliding. In fact, the reason is this makes sense because in the rotational motion, when an object is rolling, this object has not only one type of kinetic energy, it has translational kinetic energy and also rotational kinetic energy. So which means total mechanical energy at the top is shared by these two types of kinetic energies. That's why if you share something, what happens? Its value increases or decreases? Of course decreases. That's why translational kinetic energy at the bottom this time will be less than sliding down. In the sliding down, completely all energy at the top, all mechanical energy at the top converted to translational kinetic energy at the bottom. But in here, all energy, all mechanical energy at the top is not converted to translational kinetic energy. Some part of it used for rotation of the solid ball. That's why translational speed of the solid ball will be less than translational kinetic energy of the sliding object. Okay, this is how we solve in a long way, but there's a hack for this types of question. I briefly show the hack to you. This hack, in fact, is coming from what I did in here. Every step in here I did will give you a hack. Proof is put in here at page 144. Because the questions all are very similar, that's why this hack will help you to solve this problem very easily. What this hack tells you, general question is about calculating the translational speed at the bottom of an incline. So you are going to write an equation which relates to translational speed in terms of H, G, and C. You know what C means, coefficient of moment of inertia. So in here I did the calculation, the proof of this one, but this is the hack which we are going to use. Root of 2gh divided by c plus 1 is the hack for calculating the translational speed at the bottom. So let's apply for this problem. G is 2, G 9.81, H is 2, C is for solid sphere, it is 2 over 5. When you insert in here, you are going to get again the same answer. That's why if you can keep this hack in your mind, okay, use this one. Don't use all these long ways, but if you are good at physics, if you're good at conservation, applying the conservation law, this is okay. But if you think that this is very, very long, so I am going to use this hack. You can also use this hack for solving this problem. That's why I am going to also use this hack, spending so much time for the next question. I am going to show you how to apply this hack equation to other problems, like practice problem, question number 1. Let's apply this hack to this practice problem, question number 1. A 1.5 kilogram bicycle tire of radius 0.33 meters start from rest. As I said, all the questions in here will tell you start from rest. That's why you are going to say that initial translational speed is 0, initial angular is 0. That's why at the top of the incline, total mechanical energy will be only equal to potential energy, kinetic energy will be 0. So rolls down from the top of a hill, which is 14.8 meter high. So that height is given to you 14.8 meters. And mass is given in the equation. In fact, in the Heck equation, we don't have mass. Mass is cancelled, but let's record again. No problem. We can record 1.4 kilogram. Radius is not needed. 0.33 meters. Start from rest, rolls down on a hill, which is 14.8 meter high. What is translational speed of the tire when it reaches the bottom? So calculate that translational speed. This is the question. And according to the Heck equation, translational speed is equal to root of 2gh divided by c plus 1. So c plus 1, in here you need two brackets. One of them is the bracket of the denominator, one of them is inside the root. Okay, so Vt is equal to, let's apply this. What is C for bicycle tire? Bicycle tire, remember, is given as a thin hoop about symmetry axis. So bicycle tire has a moment of inertia equation, mr squared thin hoop about symmetry axis. And the problems they are giving these equations, especially 99%, it will be given. Okay, so but what is C in here? In here, there is one you can't see, but one is normally not written. There is 1, which means C is equal to 1 in this equation, mr squared. Instead of C, you are going to write 1 and you will find the answer. So 2g, g is 9.81. H is given as height of the incline, which is 14.8. Divided by C is 1 plus 1. So when you apply your calculator, you will get the answers of this problem as, I think, 12.1 meter per second. And translational speed at the bottom is going to be 12.1 meters per second. So as you see, Heck is much easier, but this Heck is only used for an object released from rest. And this is important. And as I said, all the problems are like this, but keep in your mind, this Heck can be used only for an object which is released from rest. According to that, we calculated this Heck. Translational speed is that, but sometimes they're asking angular speed. Can I get the angular speed? Yes, because I know that if I get Heck by Heck translational speed, angular speed is going to be, we know that translational speed is r times omega. In the case of omega is asked, just apply this equation. So then divide by r, omega is going to be Vt over r. Okay, one of the chapter questions asking you omega, not Vt. Many problems, sample problems, practice problems are about the translational speed. But one of the problems in the chapter review is about omega. When you see omega, don't get surprised. First, use your Heck to get translational speed. After that, apply this equation, second equation, for calculating the angular speed at the bottom. Let's solve one more problem, and then a regulation basketball has a 25 centimeter diameter, may be approximated a thin spherical shell. Yeah, which means you are going to use moment of inertia of thin spherical shell for basketball. Remember that equation, 2 over 3 mr squared. That's why C is for basketball is 2 over 3. So diameter is given 25 centimeters. So radius must be half of it. So let's record it. Radius is 12.5, which means 0.125 meters is the radius of this regular basketball. Maybe approximated a thin spherical shell. So C is equal to 2 over 3. How long will it take a basketball starting from rest? Again, starting from rest, so you can use Heck to roll without slipping 4 meters down an incline. This is important. 4 meters down an incline is not defining the height. 4 meters down an incline is defining the length of the incline. This is L. L is 4 meters. That's why you should first get the height. So L, length of the incline is 4 meters, and then that makes an angle of 30 degrees. This angle is 30 degrees. So calculate how long will it take? And from here to there, what is delta T? So calculate delta T. Okay, to calculate delta T, you are going to use kinematic equations for accelerated motion because this ball is accelerating along this incline. So first you should use this kinematic equations. Remember, we have 4 kinematic equations for accelerated motion. We are going to use that, but first I have to get what is the final translational speed at the bottom of the incline, because I know that initial is 0. So if I know final, I can use one of the kinematic equation for calculating delta T. So let's use the hack first. Let's get what? Get final translational speed at the bottom of the incline. So root of 2gh divided by c plus 1. Insert the given into the equation. 2g is 9.81. h is we should calculate h. The given is not h, the given is L. So we should first get what h is. How can I get it? This is a right-angled triangle. Right-angled triangle, and hypotenuse is 4. I have to calculate opposite leg of the angle. Opposite leg is calculated by hypotenuse multiplied by sine of the angle, sine 30. Hypotenuse is 4. Sine 30 is 1 over 2. So it is 2. Height of the incline is 2 meters. So now I can use h. H I calculated 2. Divided by c plus 1. What is c for spherical shell? It's 2 over 3. 2 over 3 plus 1. As I said, you are going to use one bracket for the denominator, one bracket for the root, and after that you will find, if you use your calculator, you can find V as 4.85 meter per second. Now you found what final speed is. You know what initial translational speed is. You know the displacement of the ball. It is 4 meters. So use the equation for second kinematic equation, which is delta x is equal to 1 over 2 V initial plus V final multiplied by delta t. Delta x is equal to 4, which is the length of the incline because this ball is following that distance. So it is 4. 1 over 2. Initial translational speed is 0 because it's released from rest. Final is, we calculated 4.85 multiplied by delta t. So if you apply your calculator, it becomes, delta t becomes 8 divided by 4.85, which is equal to 1.65 seconds.